Students. In this lecture video, we will discuss about step response and impulse response of a system. Basically, the problem is if I have an input xt here and I have a system with impulse response h of t and an output y of t, then if we are given a differential equation relating the input signal x of t and the output y t, how can we determine the step response and the impulse response of the system? So we have this example. This is a system described by a first order differential equation, dy of t by dt plus 5yt is equal to x of t. Determine the step response of the system and the impulse response of the system. Okay, actually, in the ideal case, the impulse response is the response where when we give a Dirac input or a Dirac of t or the impulse function Dirac t. However, usually a step signal is applied and the step response can be found from that step signal input, and then from the step response we can derive the impulse response, as I will show you step by step. Okay, so as I said here, if I have an input Dirac t to the system, then the output is y of t, x of t convolved with h of t, Dirac t convolved with h of t, which will give me h of t. This is because any signal convolved with the impulse function will give you the same signal. So here we give the impulse and the output is h of t, which is the impulse response. Actually, that's why we name it as the impulse response, because it is a response for an impulse input. Now, let's find the step response of the system. The step response of the system means if I give ut to the system, which is, as you know, u of t is equal to 1 for t greater than 0 and 0 for t less than 0, which is a unit step function, then what is y of t? Let's follow the steps of convolution. Y of t is equal to x of t convolved with h of t. Then from minus infinity to infinity x tau ht minus tau d tau. So x tau now is our u of t. Okay, our u of t. Now using convolution commutative property, this is also the same as ht convolved with xt, which is h tau xt minus tau d tau. Why we do this? Because the h of t is not given here, but u of t is given, so it is easier to flip and shift the unit step signal, which is already known. So this means xt minus tau means ut minus tau h tau d tau. So what do we have to do this convolution? First, we have to have u tau, we flip it and we shift it. U tau means, so u tau, you flip it, you get u minus tau, and you shift it, ut minus tau. U tau is this, your axis is tau now, so it is 1 for tau greater than 0, like this. And what is u minus tau? We flip it across the y-axis, okay? So the right goes to the left goes to the right, and I have u minus tau. So u minus tau is equal to 1 for tau less than 0 and 0 for tau greater than 0. Now, the next step is a shift. We shift it and we get ut minus tau. Ut minus tau means, for example, if t greater than 0, shift right, and t less than 0, shift left. Here is just, for example, we have t greater than 0, and we shift it to the right. So ut minus tau is different from 0 from minus infinity until t. Until t it is 1, but for tau greater than t it is 0, as you see from this graph. Okay, if I multiply this, remember here is product of ut minus tau times h tau. What will happen when I multiply these two functions? Okay, so the multiplication is point by point. That means every time step is multiplied from t minus tau function and h tau function. So when we do the multiplication, whatever I have for h tau, after tau greater than t, the product will be 0. Why? Because ut minus tau is 0 for tau greater than t. So the product of the multiplication will be 0. However, for tau between minus infinity and t, this is 1. So 1 times h tau will be the same h tau. Therefore, the interval of integration this becomes from minus infinity until t, and we remove ut minus tau. Why we removed it? Because it has no significance anymore. We already got the interval of the integration and the amplitude is 1. So what do we get at the output? At the output we get the integration of the system impulse response from minus infinity to t, h tau d tau, which means when I give a unit step input, at the output, I get the integration of the impulse response, the integration of the system. This is interesting, actually. If you remember, the unit impulse, u of t, is the integration of Dirac function, the impulse function. Okay? With the same analogy, we got if I give a unit step input, here I get the integration of the impulse response at the output. Okay, so the step response of the system is the integration of the impulse response of the system. So S of t, let's call it S of t, the step response is from minus infinity to th tau d tau, which means if I differentiate this, the derivative of S of t, the derivative of S of t, derivative will cancel the integration and I will have h of t. Okay, so the derivative of the step response gives me the impulse response. Similar to this one, the derivative of unit step will give me the unit impulse function. Okay, the derivative of unit step will give me the unit impulse function. With the same analogy, the derivative of the step response will give me the impulse response. That means if I am asked to get the impulse response of the system, because it's difficult to solve the differential equation with an input Dirac t, which is the impulse. Okay, it's difficult to solve this equation with the input x of t is equal to Dirac t. Okay, so what normally we do, we give instead unit step function, and at the output we get the step response of the system. Once we get the step response of the system, we differentiate the step response of the system to get the impulse response of the system. Okay, so this is the concept. So now you understand the concept. Let's do the previous example. Okay, now this is the differential equation for that system. find the step response and the impulse response. Okay, one more thing. When we calculate the step response of the system here, we assume the initial condition is 0, because also for the impulse response of the system, the initial, when we assume the impulse response is 0. So because this is also a differential equation, first order differential equation, then we need one initial condition, and that is the value of y at 0, which is we assume y at 0 is equal to 0. Now we follow now the as we studied solving differential equation, we follow the steps for that. The complete solution is the homogeneous solution plus the particular solution. The homogeneous solution means with the input is equal to 0, and first we get n is 1, a naught, the coefficient of y of t 5, a1, the coefficient of dy of t by dt 1, b0 is 1. So the homogeneous solution is from I is equal to 1 until n ci e to the power of rit. That's from 1 to 1. It will become c1 e to the power of r1t. So I will have one root. And from the characteristics equation or the polynomial equation, we have from k is equal to 0 to n, a k r power of k is equal to 0. From k is equal to 0 to 1, a k r power of k is equal to 0. And we expand this. A naught r power of 0 plus a1r is equal to 0. A naught is 5, a1 is 1. So 5 plus r is equal to 0 and r equal to negative 5. Therefore, the homogeneous is yh of t c1 e to the power of r1t, c1 e to the power of 5t. So we found the homogeneous solution for the unit step input. Then the next step is the particular solution. Okay, remember the particular solution will have the same form like the input. So we have a unit step input. So yp of t is equal to cpu of t. So what is cp? The question is now what is cp? We substitute here. And what is the derivative of yp? We solve for t greater than 0. The derivative of cp, the constant, is 0. And 5 times yp is equal to x of t. That means, okay, the derivative of cp is 0. 5 times cp u of t is equal to ut, which means from this relation, cp is equal to 1 over 5. Now we found the complete solution for the unit step input, which is equal to c1 e to the power of minus 5t plus 1 over 5 u of t. So what is left? C1 is missing. So how we solve it? From the initial condition, as we said earlier, y at 0 is equal to 0, which means y at 0 is equal to c1 e to the power of 0 plus 1 over 5 is equal to 0. c1 plus 1 over 5 is 0. So c1 will be negative 1 over 5. Okay? So with this, we completed and we found the step response of the system. So let's put it now, c1 negative 1 over 5. And if we rearrange, we have y of t 1 over 5, 1 minus e to the power of 5t ut. If you see what kind of output is this, is it a decaying or growing exponential? It will be a growing because this part is decaying. Why? Because of the minus 5t. When t goes to infinity, this will be e to the power of negative infinity, which is equal to 0, and it will be 1 over 5. And this is s of t, the step response of the system. Okay, exponentially growing function with the limit when t goes to infinity, it will become 1 over 5. Now from this we can get the impulse response h of t, the derivative of s of t for t greater than 0, because for t less than 0, this is 0. So the derivative of 1 over 5 times 1 minus e2 minus 5t, the derivative, which is the derivative of 1 over 5, and the derivative of this part. The derivative of 1 over 5 is 0. The derivative of this part is minus 5 over 5 this, and this will be positive. 5 will cancel 5, and it will be e to the power of 5t for t greater than 0. So the impulse response h of t is e to the power of 5t ut. So this is the impulse response. We got it from the step response. As I said, normally it is difficult to get the solution of the differential equation if the input x of t is Dirac t, the impulse function, but we found it indirectly first by getting the step response and then the impulse response. If you compare the two, this is a decaying exponential function and this is a growing exponential function. And in lab 3, solving first order systems, we have in ECEN221 finding the step response and the impulse response of a system. So we need this theoretical mathematical analysis to solve first the lab exercise in ECN221. This is how you get the theoretical formula. And you get, by following these steps, you solve that differential equation in the lab 3 exercise. And after that, you will find the theoretical equation and you compare it with the simulation, which is the step response, using the step function and the impulse function. That's all about this lecture about step and impulse response. Hope you understand the concept. You can apply for other differential equations to solve the impulse and step response of the system. And thank you for listening to the lecture.